The James Webb Space Telescope is not unsettling because it sees farther. It is unsettling because the farther it sees, the less the universe looks the way it was supposed to. We turned Webb into a triumph story, a 25-year engineering miracle. $10 billion in a gold-coated mirror the size of a tennis court, folded like origami, and launched into a gravitational equilibrium point 1,000,000 miles from Earth. The photographs were breathtaking. Galaxies, nebulae, colors that felt almost too vivid to be real. We framed it as confirmation that human ambition could reach the edge of time itself and return with images. We made it feel like an answer. A powerful, expensive, extraordinarily beautiful answer. That is the version most people carry. And it is not wrong, exactly. It is just dangerously incomplete. Because in the first years of Webb's operation, it did not only return images, it returned data. And the data did not confirm what the models predicted. It contradicted them, not at the edges, not in minor adjustments requiring a footnote, in places that physicists are still struggling to explain without pulling on threads that unravel something much larger. Here is where the real story starts. Not in the photographs, not in the press releases. It starts in a framework that cosmologists spent decades building. A framework so successful, so precisely confirmed by observation after observation, that most scientists considered its foundations settled. That framework is called Lambda CDM. It is the standard model of cosmology. It describes a universe that began approximately 8 billion years ago in an event of incomprehensible density and temperature, expanded rapidly, cooled, and over hundreds of millions of years allowed the first atoms to form, then the first stars, then the first galaxies. Each step emerging slowly in a sequence governed by gravity and time. Lambda CDM is extraordinarily precise. It predicts the temperature and distribution of the cosmic microwave background, the faint afterglow of the early universe, with accuracy that has been confirmed by satellites including COBE, WMAP, and Planck. It predicts the large-scale distribution of galaxies across the observable universe. It has been the most successful model of cosmic structure humanity has ever produced. And then Webb looked at the early universe and found things that were not supposed to be there, not absence, not darkness, galaxies, fully formed, surprisingly massive, unexpectedly bright galaxies, appearing in a period so early in cosmic history that they should not have had enough time to exist. The universe, according to Lambda CDM, was simply too young at that stage to have assembled structures of that size and complexity. Star formation takes time. Gas must cool and collapse. Stars must live and die and seed the next generation with heavier elements. Galaxies must grow through mergers and accretion across vast timescales. That is the sequence. That is the model. And yet, what Webb found, at redshifts corresponding to a universe only a few 100 million years old, were galaxies that appeared to have already undergone that entire process. Not just once, many times. Astronomers refer to them informally as impossibly early galaxies. That is not a metaphor. It is the actual language researchers used in published papers. One study, published in Nature Astronomy in 2023, identified 6 candidate galaxies with masses comparable to the Milky Way, appearing at redshifts above 7, meaning the universe was less than 700 million years old when their light was emitted. That does not sound alarming until you understand the constraint it places on cosmology. For galaxies that massive to exist that early, star formation in the early universe would have had to proceed at an efficiency approaching 100%, meaning nearly all available gas would have had to convert into stars almost immediately with almost no waste. That does not match any simulation built on Lambda CDM, not approximately, not even close. Erica Nelson, one of the researchers on that study, described the findings directly. She said, "I was not expecting us to find something like this. It's bananas." That is a tenured astrophysicist at the University of Colorado, describing peer-reviewed observational data, with that word. And she was not alone. Researchers at institutions, including the University of Edinburgh, MIT, the University of Texas, and the European Southern Observatory, began publishing analyses all pointing at the same pressure point. The early universe, according to Webb, was more structured, more mature, and more chemically evolved than the timeline allowed. This is not a fringe interpretation. It is an active debate in serious cosmological literature, and it does not stop at galaxy mass. Webb has also returned spectroscopic data, direct chemical fingerprints from light, suggesting the presence of heavy elements including carbon and oxygen in galaxies at redshifts that imply a universe barely 1 billion years old. These detections are still being confirmed observation by observation, and researchers are careful about their conclusions. But the signal keeps appearing. Heavy elements are produced inside stars and distributed by supernovae. Their presence implies generations of stellar evolution had already occurred, and the timeline, as currently written, left almost no room for those generations to have happened. The model does not explain it. The model was not built for it. That does not mean the Big Bang did not happen. What it does mean is something more precise and in some ways more interesting. It means the part of the model that describes what happened after the Big Bang, how quickly structure formed, how efficiently gas collapsed into stars, how rapidly galaxies assembled, may be wrong. Not wrong in the way that needs a small correction, wrong in the way that requires a structural rethink. And physicists are not hiding that. The debate is happening in public, in journals, at conferences, in preprints. The question is not whether Webb found something unexpected. It did. The question is what category of unexpected it is. Is it a measurement issue? Are some of these redshifts slightly off? Are the mass estimates inflated by active black holes making galaxies appear brighter and more massive than they are? Is it a modeling issue? Do the simulations simply underestimate how efficiently early galaxies formed? Or is it something deeper? A crack in the foundations of the standard model that requires introducing physics we do not yet have. None of those possibilities have been ruled out. All of them are being seriously investigated. And here is what makes that genuinely uncomfortable. Even the most conservative explanation requires acknowledging that the universe was doing something in its earliest stages that we cannot currently reproduce in any simulation or account for in any existing model. So here is the question worth sitting with at this exact moment before the story goes further. If the universe managed to build structures in a few 100 million years that our best models say should have taken billions, well, what does that say about how well we actually understand the relationship between time and complexity? And what else might be out there at redshifts we have not yet reached that we have not accounted for? Leave your answer in the comments. The range of what people are saying about this is genuinely worth reading. Then stay, because the next part is where the implications stop being about galaxies and start being about the model itself. Consider what lambda CDM is built on. At its core, the standard cosmological model relies on two components that have never been directly detected. The first is dark matter, a form of matter that interacts gravitationally but does not emit or absorb light. Its existence is inferred from the way galaxies rotate. From gravitational lensing, from the large-scale structure of the universe, it is not a fringe idea. Most cosmologists consider it the best available explanation for a range of well-confirmed observations. But it has never been directly detected in a laboratory. Every purpose-built direct detection experiment has come back empty. The second component is dark energy, a term for the force or property of space driving the universe's accelerating expansion. It was inferred from supernova observations in 1998, confirmed by multiple independent lines of evidence, and rewarded with the Nobel Prize in Physics in 2011. But what dark energy actually is remains entirely unknown. Together, dark matter and dark energy account for approximately 95% of the total energy content of the universe, according to lambda CDM. And here's the part that deserves a moment of stillness. The model that describes the entire history of cosmic structure, from the first moments after the Big Bang to the present, rests on two components that we have named, mapped indirectly, and built entire simulations around, but have never directly touched, seen, or measured in isolation. That was already a remarkable admission before Webb launched. And now Webb is returning data suggesting that even within that framework, the timeline of structure formation does not fit. The problem may not be the Big Bang itself. The problem may be nearly everything we assumed came after it. There is a version of this story where the resolution is mundane, where spectroscopic follow-up observations refine the redshifts, where improved stellar population models explain the apparent mass excess, where lambda CDM survives with adjustments and cosmology continues. That version is possible. Serious scientists hold it. But there is another version, one that is also being seriously discussed at institutions including the Kavli Institute for Cosmology at Cambridge, the Canadian Institute for Theoretical Astrophysics, and the Flatiron Institute in New York, where the Webb findings represent the beginning of a genuine paradigm pressure. Not a revolution yet, but the kind of accumulating tension that historically precedes one. Cosmology has been here before. In 1998, two independent teams measuring supernova brightness discovered that the expansion of the universe was accelerating, a result so unexpected that the lead researchers initially thought they had made an error. They had not. The universe was doing something the model could not explain. Dark energy was proposed as a placeholder for something we did not understand. That placeholder is still standing more than 25 years later, because nothing better has arrived. Webb may be generating a new placeholder situation, a new region of the map marked with the honest notation of empirical science. Here there be things we cannot yet explain. We spent decades making cosmology feel complete. Textbooks printed timelines of the universe, the first 3 minutes, the first stars, the epoch of ionization, the formation of the cosmic web, as though those chapters were closed, their contents confirmed and filed. We made the Big Bang feel like settled history, ancient, remote, safely understood. A story that started 8 billion years ago and led, through a sequence of well-mapped steps, to the galaxy you live in, the star it orbits, the planet it warms, the moment you're in right now. We made it linear. We made it legible. We made it feel like a timeline on a wall rather than an open question in a room full of people who are still arguing about the furniture. Webb did not disprove that story, but it did something that may matter more in the long run. It pointed a mirror at the part of the story we assumed we understood and showed us that something in it does not add up, that the universe, in its earliest observable moments, was doing things that none of our models predicted and none of our simulations can reproduce, that the structures we see at the edge of time should not be there, not according to the timeline we built, not according to the physics we mapped, not according to the 95% of the universe's content that we named but cannot find. The telescope is not broken. The universe is just older in its complexity than we were prepared to see. And the part that should sit with you, the part that does not resolve cleanly into a press release or a headline or a reassuring conclusion, is this. Webb has only been operational for a few years. It has covered a small fraction of the sky. It has confirmed a handful of its early anomalies with spectroscopic follow-up and found that they hold. The rest are waiting. More observations are scheduled. More redshifts will be measured. More impossible galaxies may be waiting at the edge of what the mirror can reach. And each one that holds up under scrutiny is not just an interesting data point. It is a crack in a picture of the universe that took a century to paint. The picture is not ruined, but the cracks are real, and no one is certain yet what is on the other side of them.